Today's last talk, we will have Anatole Gallouët from Grenoble, who will talk about numerical resolution of Jacobian equations. So please, Anatole.
Thank you. So first of all, thanks to the organizer for this conference. I'm super happy to be here in Lisbon. So I'm going to talk about Newton algorithm to solve semi-discrete generated Jacobian equation. So this is a joint work with my PhD supervisors, Quentin Mérigot and Boris Thibert. The generated Jacobian equations are, in sort of way, generalizations of optimal transport problem that were introduced by Schrödinger in 2014. They arise from a non-imaging optics problem, inverse problem in non-imaging optics. So what I'm going to do is starting by introduce to you this problem in non-imaging optics, and then see how it comes to generated Jacobian equation and how we can solve them. So first of all, what are non-imaging optics? So if we are, the inputs of the problem are a light source, which will be represented by a measure mu, and a target, which will be represented by another measure nu. And the aim of the problem is to construct a mirror surface that will reflect the measure mu towards nu. So this is an inverse problem because the original problem would be obviously to compute, to have the light source and the mirror, and to compute the target, which would be derived by Snell's law. Okay, and in our setup, what we'll consider is what we call the semi-discrete setup. So the light source we will choose here on this drawing is in 2 dimensions. So the light source will be a domain omega and with an absolutely continuous measure mu, and our target will be a finite target. So it will be a set of points, and the measure nu will be a sum of weighted Diracs. And obviously, to have a well-posed problem, we need the mass balance condition, which is that both measures are the same, both space are the same total measure, so we can consider them as a probability measure. Okay, so now I'm going to present our first non-imaging optics problem. So this is the far field reflector problem. So here, what I'm going to consider is what we call a collimated source, which means that all the rays emanating from light rays emanating from that source are directed vertically, so they are all parallel, and the intensity of the light ray emanating from x is mu of x. And my target will also be direction, so I can consider them on the sphere. And so I'm aiming at direction, which means that I'm aiming at direction at infinity. So if I choose, if I had in the simplest problem one unique direction, well, the obvious solution would be to have a plane that reflects all my rays toward the same direction. And now if I have several directions, it is quite natural to choose my mirror to be plane by parts. And if we impose this mirror to be the maximum of planes, then we get that this mirror will be parametrized by a function u, which is a maximum of affine functions. And each part of the plane will reflect all the rays toward the same direction.
Sorry, just to be sure, so the problem is scalar measure in the input because all the source is parallel.
The source is completely parallel, so all the rays are vertical, emanating from the same plane, and my target are the direction at infinity. So if I choose this parameterization as the maximum of planes, then I can project each part of my mirror on my light source. And if when I'm computing this projection, I get like a partition of my plane, which is what we call visibility cells VI, each one associated to a direction target YI. And thus VI is parameterized by all the point X, where this plane is higher than all the others, so it is the maximum of affine function again. And the aim of the far field reflector problem is to compute the heights of the mirror Ci, which are my variable, and I kind of forgot to explain this, but obviously I'm gonna choose different heights for my different plane to aim different targets. And this is what going to impose that my mirror will have a bigger plane toward this or this direction and have a bigger visibility associated to each direction. And so the far field reflector problem consists in finding a variable psi, which is all the heights associated to each direction. So if I have n direction, I have n height of mirror. And if I want to find psi such that the measure of each cell is equal to the measure of each direction targets. Okay, so as you can see in this visibility cell, the function is linear in psi. So actually, this is an optimal transport problem in its dual form and in the semi-discrete setting. Okay, and now if I'm going to consider another problem which is very similar. Actually, so I'm going to represent it in 2D for simplicity, but it's very similar. The light source is exactly the same, so it's collimated. All the rays are going vertically, except that here, instead of targeting direction at infinity, I am targeting points that are in the same in the same plane as my source. And so now on, I'm not going to choose a plane that aim at infinity, but pieces of paraboloids for which the focal point is the points on my target. So any ray that are going towards the same paraboloid will be reflected toward the same point. And if I make the same imposition that I want my mirror to be maximum of these paraboloids, so I want my mirror to be maximum of n paraboloid, where n is the number of target again, then I get a parametrization function for my mirror that is a maximum of paraboloids of this formula. And my visibility cells now are quite the same. They still form a partition of my light source omega, except that here they have this form, which obviously is not linear in psi. So again, the near field reflector problem here is to compute my variable psi so that each cell has the correct measure. But this is not linear in psi, so we cannot write it as optimal transport, and which is why we brought the framework of generated Jacobian, which is just a little bit more complicated, but has globally the same form. So just to give you an idea, if we compare the visibility cells for the two problems, for the first one, we basically have a weighted Voronoi diagram because all the intersection between planes are straight lines. And in the second one, we have intersection of paraboloid that are projected on a plane. So this is what we call a Möbius diagram, which actually has an intersection that can be either straight lines or circular arc of a circle. Sorry. Now for my global framework. Okay, so I'm gonna need to have a generating function, which is which will be necessary for defining my visibility cell, and it needs to satisfy the several hypotheses. So we have a generalization of the twist hypothesis that is well known in optimal transport, and we need regularity and monotonicity condition. And once we have a generating function, we can define a generalization of the Laguerre cells, which is basically what we saw before as the visibility cell. It is the point on the light source where my generating function is bigger, is the greater at y than all the other j from the target. So for the far field reflector, for the far field parallel reflector problem, we have generating function that was the scalar product. And in the near field case, we had this function. Actually, if we replace the scalar product x scalar p in this formula by a function cost of c of xy, we exactly get the framework of optimal transport. And once we have our generating function and our generalized Laguerre cell, the semi-discrete generated Jacobian equation consists in finding my dual variable psi, such that the mass function defined by the mass of each Laguerre cells correspond to the target measure. Okay, so the mass of each cell here must correspond to the mass associated to the to the point I'm targeting here. So this is a generation of optimal transport in a dual form. And now what we are going to do is try and solve this equation using a Newton algorithm. So basically what we want to do is having h of c minus nu equals to 0. And for Newton, what we need to have is to show that h is C1 so that we can do a first order development. So this is the main results that of the article we are publishing with my advisor. So under an hypothesis of generosity on the target Y, we have that H is of class C1, and we have an explicit formula for the derivative of H, which is the integral over the intersection between two Laguerre cells of a continuous function. This function is continuous because of my hypothesis on my generosity function, generating function. And the main difficulty of this proof was to show that each intersection between two cells evolves continually when we perturbate it a little. So we don't have any like disparation or apparition of intersection between two cells. So once we have these results, what we can show is that if we place ourselves on the set where all the cells have mass, there is no empty cells associated to one point in the target, then the differential of my function h is of rank n-1, and I know the form of its image and its kernel, which allows me to define my descent direction for Newton algorithm with adding a line actually that it's never of rank n, because in the case of optimal transport, you can see that if I take a mirror and just displace it by moving all the planes above or all the plane below, which consists in adding a constant to my variable psi, then it will reflect the light towards the same way. So it won't be of rank n. Actually, if I have paraboloids, it's a little bit more complicated than that, because I cannot just shift the paraboloids since they have focal points that are fixed. But there exists a vector, which is this vector W in the kernel of my matrix. There exists this vector, which if I displace all the paraboloids with the good values, then I will have this exact same reflection. So I will never have an invertible matrix, but we can see that we can show that it's of rank n-1. And if I fix one of my parameters, which consists here in fixing one variable to 0, then I have a unique solution, and so I can have a unique descent direction. Once I have a unique solution for this system, I can write my Newton algorithm. So actually, numerically, obviously, we need to impose that there is always a little mass. We cannot have a strictly superior to 0, so we need to impose a little mass in each cell. And once we have that, we are going to damp our Newton algorithm with the parameter tau, such that at each iteration, we need to ensure that we are going in the right direction, so that our function is decreasing towards 0, and that we stay always in the admissible set, which is that there are no cells that shrinks to the empty set, or I would not have my differential that would be a rank n-1. It could be a rank n-2, which won't work for my algorithm. So I have this damping parameter. And we have a theorem that is that under always some assumption of y, we have the convergence in a finite number of states. So actually, the proof of this theorem is a proof by compactness. So if we define all the variables that are in my admissible sets and which have a norm that decrease, then it is non-empty and it is compact. And since my parameter tau, it can be shown that it varies continuously in psi, I can bound it below on my compact set, and so I obtain linear convergence for my damped Newton algorithm. And actually, what we observed numerically is that in most of our tests, the parameter tau k quickly equals to 1. And once it is equal to 1, we have a classical Newton algorithm, and then we obtain quadratic convergence, which we cannot prove, but which we have often in our numerical experiments.
But then what do you need finite number of steps? Linear.
We have linear convergence, and so it converges in a finite number of iterations. Like k is finite.
Because you have a precision.
Yeah, obviously for precision epsilon, it's not. You're right, it's not precise here, but yeah, we never get the exact solution. It's numerical. And so we've implemented this algorithm for the near field reflector problem. So if you recall the problem, I had my paraboloids and wanted to compute like a focal distance such that my Laguerre cells had the correct mass. And to do so, the main difficulty is actually to compute this diagram at each iteration. And to compute this diagram, what we did is we used a result that was published by Bossona, Wamser, and Ivinek in 2007. So if I have a Möbius diagram which has this form, which is a little more general than the form of my diagram, because I had like 1/2 psi for lambda and p/2 for mu I. And if I have a Möbius diagram, then I can compute it by computing a power diagram in a dimension d+1 and intersecting it with a paraboloid. So this is what this result tells you, is that if BI is a Möbius diagram, then by considering pi the projection of the RG+1 on RG, the orthogonal projection, then my Möbius diagram VI is the projection of my power diagram in RG+1 and a correctly chosen paraboloid, which is the paraboloid centered in 0. So once we had this result, we could compute the Laguerre cells, and so we could test our algorithm. So here's the image of a test for 5,000 points in my target. So this is just the Laguerre cells. I haven't plotted the mirror. So at the initialization of our algorithm, I had all my my points in my target that are in the upper right square. So I have cells that are way bigger than others. And what we are trying to compute is we had an uniform measure as a target. So we wanted cells that are mainly of the same mass. And so this is what we get as a result. And as I mentioned, we also have like the number of iterations depending on the number of points on the targets. And so this is why I mentioned earlier, you can see that at the beginning, we have like a damping parameter that is low. And so we have a starting convergence that is low. And once the algorithm has getting in the right direction, well, the damping parameter is equal to 1 and the convergence is way faster. So in conclusion, what we did is adapting an algorithm that already existed for the optimal transport to generated Jacobian equation, proved its convergence, and implemented it in one case. And the perspective to this problem is to prove the uniqueness of the solution. Actually, as I mentioned on the set of when you have like mass in all the cells, so you have a differential that is of rank n-1, and you fix the parameter, we have a unique descent direction. So it is highly probable, we really believe that you have actually, once you fix the parameter, you have a unique solution, which is the case in optimal transport. And we haven't shown it yet for the generated Jacobian equation. Thank you for listening to me. I finished.
Any questions? Sorry, I cannot see the internet. So internet, if you want to say something, just unmute yourself. No, I think you should be able to do that on their own. Thomas, I know you're here. Thomas. Yeah, you have to.
I'm here, yes, but I can't.
Oh, yeah. Go ahead. Ask a question to your brother.
No, I can't do that.
Okay. Well, I have one. Why parabolic mirrors? Is it just because they're easy to manufacture?
Actually, it's because if you have.
Oh, sorry. Yeah.
So we choose parabolic mirrors because if you have all the rays are going vertically, And if you choose one parabole with one focus point, all the rays coming vertically are going to be reflected toward the same direction, which is the exact generalization of the plane that reflects everything toward the same direction. Then you reflect everything toward the same point. And so this is what we choose. The question that could be asked was why a maximum of paraboloid while the infimum would be a convex function, so a little more smooth. Actually, it's because when we fixed one of the paraboloid, we like to fix it above the whole source. So we are sure that the mirror is always above the source since we chose a maximum, which would not be the case if we chose a minimum, because during the algorithm, it could shrink toward below the source, and this wouldn't have a physical meaning.
Right.
I'm not sure if I'm very clear.
Yeah. And what if the source is not completely parallel, but close to parallel, like all the rays are within the cone of small aperture or something like that?
Actually, if you have physically issues like this, then it is better to choose the optimal transport problem and to pick like planes and just try to compute as many planes as possible to like converge toward. So there's a heuristic that has been found by both my directors, Boris and Quentin, which is that by solving several optimal transport problems, you can kind of converge toward the solution of generated Jacobian equation. But this is work in progress because there is no proof that the result actually converges. Just it does so numerically, but there's no proof of convergence. Question from Max.
So is this not something like an optimal transport problem where you have an additional constraint on the structure of the transport map? Like you could say, I'm doing an optimal transport problem where I confine the transport maps like a Monge problem, but I confine to the set of piecewise linear functions or something like that.
So the generating Jacobian equation is a Monge-Ampere equation, but actually you can show that when my Laguerre cells have this form here, it can be shown that this cannot be written as an optimal transport problem. But it's indeed it's slightly more general, and so you have to introduce this generated Jacobian equation in order to write them as a Monge-Ampere equation. And there's a really good survey that was written by Nestor Gillen if you want to know more about generated Jacobian equation, which covers the whole framework.
Any more questions? Okay, so if not, let's thank Anatole again. And I think we're done for today. So let's reconvene tomorrow morning at 9:30 Lisbon time.
I see you, Leonard.